Welcome back to constrained optimization using the method of Lagrange multipliers. We're going to look at this as a next example, but I want to invite you, at least if you're interested in doing this, to repeating this question using the earlier methods of single variable optimization. So the way you would do that is you would isolate for x, get x all by itself from the constraint, and then rewrite your objective function, the thing we're trying to maximize, entirely in terms of y. And then they have a single variable function. You can use single variable calculus to find the max and min. So what you'll find is it's likely easier than what we're about to do, but what we're about to do is more general. It can be used in situations where the constraint cannot be used to reduce the objective function to be one variable. So our procedure, our recipe, begins with the construction of the Lagrange function. Well, it's kind of misleading. It begins by checking the constraint and making sure it's written as g of x, y is equal to 0. So I'm going to highlight that. It's kind of a step 0 if you want. Step 0. Make sure constraint is of the form g of x comma y equals 0. And it is, so we're good. We're good for step 0. Now step 1, we're going to construct the Lagrange function. Capital F. Capital F is equal to our objective function, little f, plus lambda times g. So our objective function, 36 minus x squared minus y squared, plus our constraint, lambda, multiplied by our constraint, x plus 7y minus 25. Okay, and then let's multiply our lambda through the bracket there. So capital F is equal to 36 minus x squared minus y squared plus lambda x plus 7 lambda y minus 25 lambda. That's a function of three variables x, y, and lambda. We're going to take all three partial derivatives, set them equal to 0, and solve the system. We're going to solve capital F sub x is 0, capital F sub y is equal to 0, and capital F sub lambda is equal to 0. So for capital F sub x, we have 0 minus 2x minus 0 plus lambda. We set that to 0. For capital F sub y, we have 0 minus 2y plus 7 lambda equals 0. And then for f lambda, we can go through it, take the derivative of each piece with respect to lambda if you want, but what will always happen is the constraint will come out. It'll always be the constraint x plus 7y minus 25 is equal to 0 in this case. That gives us three equations, three unknowns. We can solve that system by using isolation. I'm going to isolate for lambda in the first equation this time. So lambda is equal to positive 2x. And I'm going to sub that into the second equation. And we get negative 2y plus 7 times 2x is equal to 0. We can add 2y to both sides. So 14x is equal to 2y. And then divide both sides by 2. So y is equal to 7x. What we do with that is we plug that into the third equation, the lambda equation. Okay, when we do that, we'll get x plus 7 times 7x minus 25 is equal to 0. We can simplify and collect like terms. We have 1 times x plus 49 times x. That's 50 times x is equal to 25. So x is equal to 1/2. Maybe not what you wanted to see, but them's the breaks. X is equal to 1/2. Now we're going to get the y value. Y is equal to 7x, which is 7 times 1/2, which you can rewrite as 7 divided by 2. Now we can check the value of the function at this point. And this is the objective function, not the Lagrange function. The objective function, little f, at 1/2, comma 7/2 is equal to 36 minus 1/4 minus 49/4. Just squaring those pieces. Square of a fraction is the top square over the bottom squared. Let's see, make common denominators. So 36 times 4, 144, minus -1 minus 49, 50, minus 50/4. So we have, let's see, 94/4 divided by 2, 47/2, I think. And that's equal to 23.5. So that's the output of our objective function at this point. Now we could check a nearby point that's on that constraint. So we could check f evaluated at, let's say, let y equal 0. Then x is 25. So 25, 0. We're going to have 36 minus 25 squared minus 0 squared. 36 minus 625, I think. 25 squared, 125 times 5. That's very negative. So if we found an extreme value for this objective function subject to this constraint, it's the max. We found the global max. And you don't need to do that step there. I include it because it's a common, excellent question. When we go through this process, how do we know if we found a max or a min? Otherwise, we don't. You need to have confidence that you did the right thing. You need to check the value of the objective function somewhere else on the boundary, somewhere else on that constraint. So I said the easiest for me, I'm going to cheat. I'm going to let y equal 0 and then solve for x, because that's the simplest. And that's why I picked 25, 0. Someone else could say, you know what, I don't care about simple. I'm going to let y equal 1. All right, so x plus 7 minus 25 is 0. Rearrange, that's your x value. Now plug that into the objective function. Let's do a second example. This is a situation where we cannot rewrite this function to be in terms of one variable. We have an objective function in terms of 3 variables, x, y, and z. We have a single constraint, g of x, y, z is equal to 0. We want to maximize this objective function subject to that constraint. So we couldn't go back to use single variable calculus for this. We're going to go through the steps, starting with step 0. The constraint is in the correct form, so we don't need to do anything to it. So step 1, we'll construct the Lagrange function. capital F. And this itself might be a question on a test. Given this objective function and given this constraint, what is the Lagrange function? And that's the whole thing. The whole question is just create it. And that, in an application, that might be the most important thing to do. Figure out what function you're trying to maximize. Okay, and then plus lambda times g. So x squared plus y plus z squared minus 16. Well, I should mention that many components of calculus are highly standardized and many components are not highly standardized. You can find resources and textbooks, other things that have the whole process, instead of plus lambda g, they write it out as minus lambda g. It's perfectly fine. It won't change your final answer. It'll change the some of the steps in the middle, but that's it. It won't change your conclusions. It's arbitrary whether you put a plus lambda g or a minus lambda g. You could even put a plus 2 lambda g. Don't tell anyone I told you that. It won't change your answer. All right, now before we proceed with taking derivatives of this, I'm going to simplify it and clean it up a little bit. 2x plus y plus 4z plus lambda x squared plus lambda y plus lambda z squared minus 16 lambda. That's our Lagrange function. And the derivatives, or partial derivatives of this Lagrange function, being set to 0, will tell us where our function could have candidate global max and global min on that boundary. Now we're going to construct system from capital F sub x is 0, capital F sub y is 0, capital F sub z is 0, and capital F sub lambda is equal to 0. And this is going to be ugly to solve. And we may need to use a different method. We may not be able to do the substitution thing. Maybe we can, but maybe we can't. All right, so f sub x, we're going to take the x derivative. We get 2 plus 0 plus 0 plus 2 lambda x plus 0 minus 0. So that's equal to 2 plus 2 lambda x. And we set that to 0. Now f sub y, that's going to be 0 plus 1 plus 0 plus 0 plus lambda plus 0 minus 0. So that's 1 plus lambda, which is equal to 0. Hey, that's pretty neat. That one's telling us what lambda is equal to. Lambda is equal to negative 1. F sub z, which is also unusual, by the way, f sub z is 0 plus 0 plus 4 plus 0 plus 0 plus 2 lambda z minus 0 is equal to 4 plus 2 lambda z, 0. And then the last one, we set f sub lambda equal to 0. This is free. We always get the constraint, so we get x squared plus y plus z squared minus 16 is equal to 0. Okay, so there's our system. So one thing that's sometimes done is all the expressions are isolated for in terms of one variable. So we would isolate the x part of the expression for x, so the first equation for x. Isolate the z equation for z, so the third equation for z, and then there's nothing to isolate for y. We just have the value of lambda. And then we would substitute in the x expression in terms of lambda, the z expression in terms of lambda. But because we don't have a part of an expression in terms of y, we can't use that type of a method here. Other examples will have a process that goes through what I just described. What we'll do in this example instead is we will use the fact that lambda is equal to 1 to get solutions for x and z, and then that will plug into the last equation, rendering it an equation just in terms of y. So from the first equation, I'll number them 1, 2, 3, and 4. From 1, we have the following. We have, from 2, lambda is equal to -1. And we plug into equation 1. And then that tells us the following. It tells us that 2 minus 2x is equal to 0. And that tells us that x is 1. We can also plug that into the third equation. Plug in the third equation, we get 4 minus 2z is equal to 0, and that means z is equal to 2. And we can plug those into the fourth equation. When we do that, we get the following. We get, instead of x squared, we have 1 squared plus y plus 2 squared minus 16 is equal to 0. So that's 1 plus 4, negative 11. Y minus 11 is equal to 0, so y is equal to 11. And we can conclude x comma y comma z is equal to the point that we just found, 1 comma 11 comma 2. We should make sure, and I didn't do this in previous examples, should make sure that this satisfies the constraint that g of x comma y comma z is equal to 0 here. So we're going to have 1 plus 11, so 12, plus 4, 16, minus 16 is equal to 0. It's true, so it's good. It meets the constraint. This point is on that boundary, so it qualifies. Now we can evaluate our objective function. F evaluated at that point, 1, 11, 2, is equal to 2 times 1 plus 11 plus 4 times 2, so 2 plus 11 plus 8, we get 21. That's our max. And if you wanted to, you could pick anything you want for x, anything you want for z, and solve for y. So maybe x is 0 and z is 0, so y is equal to 16. So you have 0, 0, 16 for an alternative point that's on the boundary. Plug that into your objective function, so 2 times 0 plus, well, so I get 16 when I do that, and that's less than 21. So I plugged in another number on the boundary, and did not get a higher value. That means that the value I found, the extreme value that I found, is the maximum type of extreme and not the minimum type of extreme. Right, and then multiple choice format. So here's that example I mentioned where the whole thing is just finding the Lagrange function. Except there's a twist. Step 0 is actually important this time. We need to put the constraint into standard form. So when we do that, our constraint, well, I should underline that. The constraint is this thing. So we have xy minus 1 is equal to x squared. And we can subtract x squared from both sides to get the constraint to be written as something is equal to 0. So xy minus 1 minus x squared equals 0. Thus, g of x comma y is equal to xy minus 1 minus x squared. Now, it might be a different order of subtraction. You might have xy minus x squared minus 1, or maybe everything moved over to the right. Whatever the case, you have to have the constraint being equal to 0. Okay, now step 2, make the Lagrange function. Or step 1, make f. So f is equal to little f plus lambda times g. Little f is our objective function, so y. Kind of weird looking, just y, but hey, that's it. Plus lambda times our objective, or lambda times our constraint, xy minus 1 minus x squared. And do we have one of those? Do we have something that looks like this? Y plus lambda times xy minus 1. Yeah, we have option A. That's it. All right, and here's another multiple choice. The whole thing's this one's the whole question from beginning to end. We have finding the minimum value of this function subject to this constraint. This one has the shortcut available if you're so inclined. You can replace the y inside your objective function with 19 minus 3x and then simplify. Take the derivative according to 1D calculus, set that derivative equal to 0 and solve for x. Plug that x value back into your simplified single variable function, and then that should be the correct answer that's here. I won't do that. I'll let you do that if you want. What I'm going to do is I'm going to solve this using this new method, and you can compare your answer to this answer. Or just trust that it'll work. Okay, constraint has to be rewritten. So step 0. We have y minus 19 plus 3x equals 0. So g of x comma y is equal to y minus 19 minus 3x equals 0. That's all we had to do, subtract everything on the right from both sides. Now we go to step 1. Make f. So f is equal to our objective function plus lambda times our constraint. Our objective function is x squared plus 2y squared plus lambda times our constraint, which was y minus 19 plus, oh, I made a typo. I see my typo. This was, oh no, yeah, my typo was here, right here. This should be plus. I don't know where that came from. I added 3x to both sides to move it over. So plus 3x. Okay, now we're going to do step 2, is construct the system. So we're going to take all the partial derivatives and set them equal to 0. F sub x is 2x. Oh, I should simplify. Multiply lambda through the bracket and make it easier to take the x derivative of it. So x squared plus 2y squared plus lambda y minus 19 lambda plus 3 lambda x. Then take the x derivative, so we get 2x plus 0 minus 0 plus 3 lambda, and we set that to 0. We have the y derivative, 0 plus 4y plus lambda minus 0 plus 0 is equal to 0. Now we have the lambda derivative, 0, 0, and then it's going to just be the constraint y minus 19 plus 3x equals 0. Okay, I'm going to isolate the first equation for lambda. So 2x is equal to negative 3 lambda. That means x is equal to negative 3 lambda divided by 2. Oh wait, I don't want to do that. I'll isolate for lambda instead. You'll see why in a moment. So I'm going to have 3 lambda is equal to negative 2x. So lambda is equal to negative 2x divided by 3. Now I'm going to plug that into the fy equation. When we do that, we get 4y plus lambda. So 4y minus 2x over 3 is equal to 0. We can get rid of the fraction right away by multiplying both sides by 3. So 12y minus 2x is equal to 3 times 0. So we're going to have 12y minus 2x is equal to 0. Then I'm going to isolate for x. I'm going to add 2x to both sides, divide both sides by 2, and I get x is equal to 6y. What we do with that is we plug that into the third equation. A key step that I didn't write down is that I didn't start by doing this. I started by trying to solve for x first. I got x in terms of lambda, and then I realized, wait a second, I can do that. I can get x in terms of lambda, then I can get y in terms of lambda. I could sub those both x and y into the third equation, then solve that equation for lambda, then go back and get x and y. So that's what I was starting to do. Then I thought, well, it might be easier to do this. It'll make it look like the other expressions. So somewhat misleading in all of this is that there is not just one way to solve these systems. There's often multiple ways. Okay, so I'm going to replace the x with a 6y. So now we have y minus 19 plus 3 times 6y equals 0. So y minus 19 plus 18y is equal to 0. Collect like terms, we have 19y equals 19. That means y is equal to 1. So we can put it all together. Step 3. We have x comma y is equal to, oh, I need the x value. X is equal to 6y. So 6 times 1, which is 6. Then we put that all together and say our x comma y value is 6 comma 1. And f of 6 comma 1. So plugging into our objective function, we have 36 plus 2 times 1, which is going to be 38. And that's one of the options. And we'll continue doing more examples in the next video.